Okay. So can you hear me clearly? Can you see my screen? Is everything?
Yeah, we can see you and we can see your screen and hear you clearly.
Okay. Okay. So let me start. So this is an introduction to root. I'll try to give some basic information about root. Then I will introduce you with root macros. Then I will try to give you some information on making graphs and histograms, and then some information on functions, about root files, root trees, and py roots, of course, if our time permits. Otherwise, I'll be uploading these slides to the Google Drive folder, and you will be able to complete the rest of the tutorial yourselves. There, in that Google Drive folder, there are also these macro files. Okay, so let's start with this. What is root and how do you install it? So root is an open source software framework. It fulfills some common computation and visualization needs of particle physics. So it's been developed in this context for particle physics needs. And also because it's being developed at CERN. Okay. This is the object-oriented age software. Before that, there was some Fortran code we were using called POW and POW. So I think that was POW++. Then it evolved to root. And root also expanded to do many things, which we will briefly discuss. Root has a graphical interface for doing interactive work, and root can be used with C++ or Python, or I'm not sure, but maybe other languages like Ruby, maybe programming languages. For example, using root with Python is very useful. So what can be done with root, with what root helps us? For example, creating histograms, one of the most basic things we need in our experimental studies. Doing graphs, graphics, curve fitting to data, so-called data frames. You can imagine these like Excel sheets, and you can do some operations on them. Very useful data structures. Root trees, these contain event data, like optimized for such tasks. RooFit is a very important package, part of root. It's used to model data with some underlying physics you provide. Root has its very complete set of machine learning code. You can do many machine learning tasks with and within root. Already spoke about this, the Python interface. Root has some very useful mathematical libraries, special functions, etc. Root has code for physics vectors and vector operations, defining them and doing operations on them. Root can recognize and define geometry, which helps, for example, design detector geometries. Okay. You can design them in root and also visualize them. You can make graphs of them. And so on, I/O concepts and signal-to-noise communications, etc. Root is very complete. You can create your own graphical user interface, like your Windows program, okay? Using root. It even has support for that. Also, very important component, root has a C++ interpreter, okay? So you don't need to compile C++ code to run access root. So about installation, this is where to go for everything root related, root.cern. And when you open that page, you are taken here I hope you can see the page. So installing root, this is the root page. For example, you can use a package manager, you can use pre-compiled binaries, you can source compile and so on. But very briefly, you can install root on like almost every operating system. Right now, I'm using a macOS operating system, but at certain Linux operating system is used. It's easy to install on Linux, also on Windows, and so on. And there are many ways to do it, and there's much freedom in how you do it. Okay? Precompiled binaries can be downloaded and directly used. You can use package managers, especially for macOS and Linux machines. I don't know about Windows, maybe there are also package managers for Windows. And you can choose to compile root for your own liking and with your own options. So let's start. Beyond this point, I'm assuming that you have a already installed root, okay, in your computer, and you have access to the terminal. So to start, I think on Windows you just double click on root exe, maybe. I never used on Windows, but on Linux and macOS, from terminal you just type root and it starts. Very important, not very intuitive. How to quit root? It's command.q. Let's look at it. So when I say root from the terminal, root starts. Okay, so this is version 6.30/0.4. And this is the root prompt here. You can enter your C++ code commands directly here. It's interactive. You can use it like a calculator here, or 5 times 8 here, and many other functions, routines, everything. It's C++. So whatever is available in root, it's available here. So this is the interactive interface. Let's see how we quit. Because when you first start root, it's always a problem. How do I exit this? So if you start with flags -L, then root won't display this welcome screen. In the old times, it used to display this as a graphical window, but I see that newer versions don't do it, which is much better. But of course, we also need the graphical interface for certain tasks. So here we started with, here's some examples that you can immediately try. Okay? Some algebraic operations. Square root function, it's recognized by an interpreter without needing to do any like include lines code. Okay, it's immediately in the current namespace. Here, this is tmath, for example. It's math library of root, and you can access to the pi function, pi number, using the error function, and so on. Are there any questions up to this point? I guess not. I hope you can access root. So root can be used interactively, as I just showed you. Root can be used with macro files. Okay? Macros, as you know, they are like a sequence of commands. Okay? Sequence of commands you give to a program. It's the same thing here. Whatever you enter this interactive shell, okay, command line, you can put all of them as a sequence and put in an inter file and run them all together, okay, as a file. That's called a macro, root macro. What else you can do with root? You can write your own C++ program and call root libraries from your program. Okay, link your program against root libraries. That's another thing you can do, which is again done quite often. This gives you very high performance programs. Macros are run by the interpreter, so they tend to run more slowly. Also, there are certain GUI applications, okay, graphical user windows. When you start something, it gives you a window, like T browser. Okay. So here, when I instantiate it, yeah. There is, for example, this root object browser. Okay, these are files, and for example, here's a root file. I can browse it like this. This is a very practical piece of code. There is also another window application like this called a tree browser. Okay. You don't need to be in the root prompt to start the object browser. It has its own standalone executable root browser. So you can run it directly without first starting with first, like this. Okay, these are how you do all the methods you can use it. Now, let me start now to discuss root macros. Okay, C++ code that can be written in root interface, interactive interface can be placed in a separate file and executed by calling it from within root. These files are called root macros. These macro files are executed by the interpreter, C++ interpreter. Okay? So they are not compiled unless you want them to be compiled. The C++ interpreter is called cln. This is an example. It's not an example in macro file, but this is the structure of a macro file. Okay? So let's say that its name is macroname.c in the file system, and this is the contents of the file. Here, there's this function, macroname. Okay? It's the same name with the file name. Here, the void function. Then here is your C++ code. This code will be executed by root. I'll show you how. Also, actually, your macro code blocks even don't need to have a function name. You can even skip this part. You don't have to give a function name, but when you give them, they may be helpful. You can skip them altogether. Okay, so in my file system, I have a macro file, let's say. Its name is macroname.c. How do I make root execute it? How do I make root run it? Run a macro, you can run it directly using the root executable, the interactive interface. Okay, for example, or you can start it directly from the command line with root and macroname like this. When you start root with the macro, it will load the macro and try to execute it. If it has no function in it, then it will just run the code block, whatever code block it finds in the file. If there is a function named macroname, then it will execute that function, macroname. And if there's none of them, there are certain functions, but their name is not macroname, then it doesn't execute anything. Okay? So this is one way to execute directly from the command line. Other way is you start root interface, and then you do this .x. Okay, so these interactive commands are root commands. Start with a dot. The first one was .q, bit. Okay. Execute command is .small x, .c. This tells you to execute this command. Okay. Third way to execute this, you start root, okay, like this. You load the file, macro file, okay, then call a function that's inside the macro file. Okay. So you can execute, you can load. There's this loading. Also, in a root session, more than one macros can be loaded in the memory. You can load more than one macros and call whatever you want from whichever macro file you load it. Here, our first example. This is the macro.c file. It's a macro. It's in the among the files I provide you in the Google Drive. This is what's inside the file. So its name is macro.c, and it does have a macro function. So when we try to execute this function will be executed, okay, directly. This function is immediately executed when you do root macro.c. What's it doing? It's just printing a message. That's it. Let's try this. Root macro.c. So it will display a message. Here. First, root started, okay, and then it starts to process this macro file. Then this is the macro function work being executed. Here, macro function çalıştı. Macro function çalıştı. Okay. Next, we can try this. See, there are two other functions in this macro file. Let's try to run them. Okay. This is exactly what I showed you that my primary display. Let's run the other two functions. Okay. First function will print merhaba. Second macro function will print ikinci function. Let's try this. F1 merhaba. İkinci function. So they were in the memory, and we can just call them. They will load it to the memory. Okay. Next thing I want to show you is how to compile a macro file. This is how you do it. You load the macro file to the memory, okay? But you put a plus sign at the end of the macros name. When you do this, then your macro will be compiled, and that machine code will be executed when you run this. Let's try this. Macro.c. Okay. So as you see, it compiles the macro. Then I can again execute it. Pardon, makro değil de makro biri demek. Şöyle. Bir göstereyim. Eksik olmuş. Ama sıkıntı değil. Şöyle. Silmenin adını makro bir duplicate edelim. So, creating shared library. Bir de içindeki makronun adını da makro bilirsem iyi olur. O zaman bir şey yapabilir. Şimdi ama makro deyince tanıyacak. Böyle bir mesaj alıyoruz yani. Compile'dan. Ve şu dosya makro bir noktasıyla SO dosyası. Farklı işletim sistemlerinde bunların isimleri, uzantıları değişebilir. Mesela Windows'ta bu DLL dosyası olabilir. Buradaki önemli bir detay şu, e, makrolarda veya bu interaktif arayüzde C++ kodları girerken bayağı bir basitleştirme var. Böyle çok, mesela include falan hiç kullanmadık bu kodlarımız, şeylerde, kodlarda. Böyle. Ekrana A diye yazdırabildim cout streamini kullanarak. Hiç böyle bir şey tanıtmadım ben. Normalde bir C++ kodunda bunun şeyini IOStream diye include dosyasının tanıtılması gerekir. İnteraktif e, arayüzde öyle bir sıkıntı yok. Yani zaten tanıyor. Ama derleme yapacaksanız, compile edecekseniz, if you will be compiling your code, okay, with this plus option, then you do need those inputs, okay? You uh, you need to add this. The reason this include is here is because I was to compile it. Normally, if you don't have no intention compiling your code, then you don't need these. Your code can be just simple. Okay, so burada da var. Orada bir karışıklık olmuş. This shouldn't be macro one. It should be macro because here in my example it's like macro.c. Okay, something mixed up. Now, why bother compiling? Why we are compiling? Because compile code runs faster. Okay, Ceiling is an interpreter and it has limitations, and your code can become exponentially slow as its complexity increases. Okay? So, but there are also reasons for using the interpreter instead of compiling, because compiling itself takes some, but when you are doing fast development, okay, like, okay, I added this feature, let me try, okay, another feature, let me try simple additions, and so on. So we can do fast prototyping using the interpreter without doing any compilation. Okay? Scripts make things easier sometimes. Using scripts, for example, you can create some shell scripts uh, which can write macros and so on, and maybe it's more useful. So you may have motivation to do both compile and sometimes compile and sometimes do the interpreter. So this was the first part of this tutorial. Now let's move on to the next part. Graphs and histograms. So how do we make graphs and histograms? Here you see some examples of this is a histogram. This is a graph, and it's along with some fit, some other histograms with fit, some limits graphs, all created with fit. So you can do such things with it. What's a histogram? If you don't know what it is, the purpose of histogram is to graphically summarize a data set. So, for example, you can have a sequence of numbers. For example, grades on a quiz, okay, all the student grades on a quiz. So when you create those bins and count how many students got those grades in those bins, and do this bar graph accordingly, that's a histogram. It's a very useful graph, kind of graph. Maybe I shouldn't say graph. Like not a relation. So it shows the central tendency of the data. Okay, so how it's like distributed, and the tendency is here in these grades, it's like between 70 and 80. The distribution, how distributed, how much variability is there in the data? Okay, is it like a narrow distribution or a wide distribution? Whether there is some skewness, asymmetry in the data. As you see, this is an asymmetric distribution, outliers, and so on. Important defining characteristics of the histogram is the number of bins. So here we have 1, 2, 3, 4, 5, 6 bins. And also the bin width, how wide those bins are. Here, all these bins are 10 grade wide. Okay. The histogram axis can both be normal and logarithmic, and the bin widths can be fixed or variable. They are all possible. Of course, histogram is not a bar chart. Okay? It's a different thing. Histogram classes in root, their names start with th. Actually, all the class names start with letter T in root, and the next letter usually refers to the specific object you are interested in. Here it's histogram, so this is th. Next number is the number of dimensions. So these are one-dimensional histogram objects. These are two-dimensional histograms, three-dimensional. The final letter gives us the data, relevant data, relevant variables for these histograms. Can be bytes, precision, short, integer, floating point, double precision, and so on. So these are the data types. Okay, so how do we actually create one histogram instance? Here an example, PH1, 1F, histogram, one-dimensional floating point, precision. This is how we create it. H equals new PH1 instance. Its name in the root namespace will be hist, and these will be, this here, hist is the name of the histogram as you recognize in the code. These are the titles of the histogram. Okay? The main title first, the delimiter here, semicolons. This is the X label, X-axis label, and this is the Y-axis label. Here. You can, if you don't want, you can skip them. But if you define them while you're creating the object, it's a good practice. Then those three numbers, their meanings are 10, the first 10. That's the number of bits. 0 and 10 are the X-axis limits. Okay, it limits the numbers that will be histogram. So the first bin will be from 0 to 1, second from 2, and so on, as confirming the numbers. A bin includes the lower limits, but doesn't include the upper limits. So if the bin has these limits, then it will include all ones, but it won't include twos. Okay. And concerning the bins, the numbering of the bins themselves, the 0th bin is the so-called underflow. It carries the number of entries that are below this number, the lowest number. There's also an overflow bin. So when you try to fill this histogram with, for example, 12, number 12, then it goes to the overflow bin, and -1, that's the underflow bin. So these are the meanings. So here, let's have this example. My code block, C++, okay. First, let's create the histogram object, H equals new PH1F. The name is hist. These are the labels. And again, it's the same code in the previous slide. Let's fill the histogram with two numbers, 4.5 and 6.7, and then let's draw it. Okay. It's in histo.c. Let's run it. Here it is. The histogram, my histogram title. Here. Okay, I didn't follow this English. Entries, boxes, and it has 2 entries. And it also gives you, this is the information box, gives you the mean of the numbers that are given as entries to this histogram. Also, the standard deviation. Here. So you can try this macro with and study that here. Now let's look at the second one, second example, macro, histo2.c. Here I have this th1fh. Here I only gave a main title, number of beans and the limits. Okay. Well, technically, these 2 objects are created differently. Here I just create a variable, th1f variable h. Here I created from the key. Okay. 2 different techniques that relates to C++. Then I instantiate this class, random number utility class, trandom. Then I have my loop, 15,000 times, looping and doing what? It's filling the histograms with random numbers that are distributed as a Gaussian. These are the Gaussian parameters, mean and standard deviation. Okay. And let's draw it. So, okay. So let's use the tool, right? Here it is. Now my histogram is filled with 15,000 random numbers, which are distributed as a Gaussian. Now the entry is 15,000. Mean very close to 0. Standard deviation very close to 7. 0 and 7. Okay. What else? We can make a logarithmic axis, for example. Let's go back to this here. Axis, the t-axis. Okay. So we can modify many things here. There is one. Oops. You need to right click not on the axis, but on the canvas itself. Okay, a blank part here. See, it's the context menu for the canvas object. You can find these logarithmic options there. Also, you don't have to do this interactively, okay, through the canvas. You can do it in the code. You can put this code, gpad, and set log y method. Then your y-axis, the y-axis of the active pad will be logarithm. It can also be done in the macro itself. That line could be added here. Okay, what else? A histogram can be multiplied with a constant using this method, histogram's scale method, constant, which is generally used to normalize a histogram. Okay, when you normalize a histogram, when you have multiple histograms, multiple distributions, and when you want to compare them, when you want to do shape comparison, You want to normalize them. You want them to have all have the same area under them. Then you can do this shape conversion. And this is how we do it. So scale is norm divided by the integral of of your histogram, sum of all the numbers. Norm is your normalization number. It can be one, it can be some other number. Then you scale your histogram with this number. Scale. So this is how you normalize your histogram. There are also other object drawing methods. For example, we can change the color of your histogram. Here, it's like a bluish color. You can change it to red, for example. You can change the fill style. Okay? You can change the line color, line style, line width, everything. Or you can do all kinds of style changes. Okay. Here, I just wanted to see if I can do it here, but set line attribute, set field marker attribute. Okay. There you go. Line. You can make it thicker. Okay. Like this. Huh. You can respond quickly and change its color. So you can also do this interactively. Okay. There are some other drawing options that are supported on our histogram. This is like drawing axes and this same, for example, is superimposed to histograms on top of each other. And so spherical coordinates, Lego drawing, and some other options for drawing. You have much of a freedom, and also here. Those options are used here while you are drawing. You put them here while you are drawing histograms. Okay. You can fit a function to a histogram. You can do this both interactively or in your code. For example, in the Canvas menu, you can use tools and fit panel. Okay. So this is my canvas. In my canvas, I have tools and the fit panel. Like this. Okay. So data set comes from the histogram. Okay. My fit function is a predefined one-dimensional function, Gaussian. Okay. All the other options, general options, minimization, which library you'll be using, so on. Just hit fit, and so it fits your histogram per function. This is how you do this interactively. Okay. Yeah, I fitted this, but what are my fit parameters? They are printed on the terminal. Here. These are the fit parameters along with their respective elements. Okay. So my fit also, for example, for sigma it's 6.96. This originally was 7. And my mean was 0. This is again very close to 0. Within the limits of the average. Okay. Now, the fit parameters are displayed on the terminal. We can do this fit in the code, in a macro, for example, or from the interactive terminal. We can use other predefined functions. There are many of them. Pol m is a polynomial of degree m, from 0 to 9, for example. The exponential function, lambda, and so on. There are many predefined functions which we can use. Here, okay, in this example, we did this fit to the first histogram. These are the fit parameters and the screen, the fit panel screen. Now, okay, we did our work. We created our histogram. We drew it. Maybe we fitted some function to it. We want to export this function, okay, to a so-called root. The root file is a special file. It's recognized by root, okay, designed to store the root software's related or created data objects. Okay? So it's a special optimized kind of file recognized by root. Here's an example code to save a histogram into a root file. So when you close your root, when you end your root session, your work, your histograms and fit and everything will be stored in that root file, and you can go back to that. Here, this line creates a new root file. Okay? It's an instance of T file object. The file name is histos.root. This option, there's a room for option here. It can be new, for example. It can be recreate and so on. Let's create a new function, new file. Then we create this histogram, okay, with the lambda distribution. Then we fill it with 10,000 random numbers here. This is a very important step. The histogram has this method, write method, that makes the histogram to be written into the root file. Okay? It's in the histogram. The method is in the histogram. You call it. If you don't call it, it's not written. It stays in the memory, and when you end your root session, it's gone. So we write it, and then we also need to close the root file, and it's there. Let's run it. So let me also show this. When we do this successfully, we can also look into the root file using a T browser, okay? Or writing a few lines of code. Let's run this. This was histo3. That's it. Created the root file. Oops, there's a crash. Here is the macro file. The file name is histo.root. Let's look into it. Oh, I can directly open it. Here you can start root by opening the root. It's immediately recognized in this session now. Attached to it. Now let's start the browser. This it's immediately here. Okay. If we didn't do this, we could just browse the file system. Okay, find the file, double click on it, and again it would come here. Here, this is the this histogram is now stored in this root file, and I'm accessing it through the root. As I've already showed, you can directly call this root browse executable to browse the root file. So that's it. That's all for the histograms. Do you have any questions regarding histograms? I guess not. Okay. So next, we continue with graphs, making graphs. In graphs, we have certain data points like X versus Y, okay? And we draw them. It's a container that contains data points. The relevant classes are these T-graph class, T-graph errors class, and T-graph asymmetric errors class. Okay? The name probably tell you something about your function. This is just a regular graph without any error bars. This is a graph with error bars. This is a graph with asymmetric error bars. Okay, so X errors can be asymmetrical from left to right. Okay, and so on. Here we have an example again. It's in the macro graph 1.c. So we instantiate the graph objects, T graph, the regular one, no error bars. Then we call this method of the graph set point. Okay? So here I need an index number. I need to give it which data point is this. When I call this get an, initially it has no data points in the graph, so it will give me 0. So this index will be 0. 0th point is 1 and 2.3. 1 and 2.3. Next, second point. Now this will be 1. This index will be 1. 2 and 0.8. 2 and 0.8. Here somewhere. And there's also a third point. Okay. This is how you manually fill your graph with data points. Then you draw it. You call the draw method. This is your drawing option. A, B, okay, it's some points. Now you set your marker style. These are markers, data markers. Here is a box square, 21. You can look at it. Okay. You can set the markers like this, a box or triangles or stars and so on. You can then change ranges, set ranges for your axes here. And you can set titles like this Z centimeter and 1 meter. Okay. And then finally, you can set titles, average vertex position. Okay. Now we can run it. 1.3. That 3 data points and all the other settings. Now let me show you something practical. If you have your data in a text file, how can you create a graph of this data? Here it's in the example macro file graph 2. Let's see. We instantiate this class directly with the file. Okay, graph dot. This is the contents of that file. Here, every line has 2 numbers. They are my data. I immediately created the graph with this file, and then I drew it again with these options: marker style, marker color, and so on. I run it. See. Certain options while drawing graphs. For example, L, it will draw a polyline between the points. Okay, when you use L. When you use F, field area is drawn. Okay, this F1, F2, and so on. A is draws the axis. Okay, so we have A. We always start with A here. This is with AP, the axis and points. You can try AL and AC. Okay. C is a smooth curve, like this, and so on. These are the graph drawing options. Root also provides certain graphing objects, okay, which you can use in your graphs. For example, lines and so on. But first, let me discuss the structure of the graphs. For example, first I have a canvas. Okay, when I draw this, so the most global object is the canvas object, C1. With the name C1. Created before T canvas, C1. And these are the canvas options. Okay, this is the most global class objects in a graph. Then in the canvas, there are pads, pad objects. There can be multiple pads in a canvas, so you can put together multiple graphs. Okay? For example, here we have this canvas, and there are two pads, pad 1 and pad 2. Maybe you produce by it concept of a canvas, and one or more pads contains. In the moment, one pad is active. GPad pointer always pointers active pad. So GPad is the global pointer. There is always an active pad. Whenever you give a drawing command, it's done on this active pad. Okay, it's like a cursor. And so on. On this canvas, we can put like text and lines and so on. We can set few colors, for example. Concerning the coordinates, for example, we have those user coordinates, so-called NDC and pixel coordinates. This is the most common one used. User coordinate system is the most common used coordinate system for paths. By default, the bottom left corner is the origin. Okay? It's usually aligned with the origin of your graph. When a histogram graph is wrong, origin of this object becomes new origin. You can define the boundary of the system using this method. So this is how we can divide a canvas to multiple paths. Like this, you have this path and you divide it by 3 by 2, 3 rows, and 3 columns and 3 rows. This. And access them separately and do things, draw things in them separately. And finally, yes, you can be drawing various graphic objects with the draw method. Okay? For example, you can draw lines. You can draw latex text, okay, like alpha, you can put normal text, other geometrical objects, and so on. So this T line object, for example, is used to draw this. It's in this is in the nesneler.c macro. We created this line object, then we drew it, then we create this text objects, okay, message hello, and we drew it, and we create this T latex object. This is how the latex code is written. Instead of backslash, we have this sharp object character, and the rest is the same. It's symbols. We do it, and we can do such additions. you can add text and these are some of the options. Labels, space, curvy lines. These are, for example, used to draw frame and diagrams. Ellipse, arrows, buttons, latex, and markers, boxes, and so on. Some of the options. Okay. Also, when multiple graphs are drawn on the same screen, okay, we need legends as shown here, okay, to show the reader which graph means what. For this, we have this class, the legend class. Okay, we define it. This is the legend's position on the pad and header. Once we instantiate this legend, then we add entries into it. Okay, these images are automatically created from the style of what you are writing here, okay? Which object you edit here. It's automatically created. That's a legend. You can set your axis labels, okay? Titles. For example, you can access the axis object using this method of a histogram object. The get x-axis method gives you the axis object. Then using that object, you can use a set a title method to set a title. Okay. Here, the example macro is axis.c. And see this inside. And finally, you will need to export this graph to a graphics file format, not a root file. Okay, I can't put a root file into my paper. I need an image file. It can be a JPEG file, it can be a PDF, and so on. So you can save your canvas as an image. When a canvas is created and drawing is ready, image can be saved in formats like PNG or PDF using the print method. Canvas is a print method. So this is the canvas.c macro example. First, we access this file, histogram.c. Okay. Then we access the H lambda histogram in that file, okay, in the H painter. Then we instantiate a canvas object instance here. And then its name is C, canvas. Then we draw the histogram. And finally, using this canvas object, we print what's being drawn with C1.video. Okay, canvas statement video. Let's try this. Canvas.c. Okay, it drew the file. Here this is C1. And PDF file C1.pdf has been created. Also canvas. Let's open it. Oops, not here. C1. Here, I have my canvas drawn in a PDF file. Okay. So next thing I want to discuss is functions, which will be used, which you may use for, again, drawing, for example. The relevant class uses TF1 for one-dimensional functions. Again, the name starts with T. F for function, 1 for 1D. Okay. There are also two-dimensional or three-dimensional functions, and F for okay. So this is how we create instantiate the object. F1, its name is fun. Okay. The namespace. So this is the function sin x divided by x. Okay. You give it as a string, and it understands it. These are the functions domain, formula, sorry, the range, function. And when you draw this, so say range değil de domain. So when you draw, call the draw method of the function object, you get your function draw. Starting from 0 to 10. And here you're drawing. This is the title, sin x over x. As usual, you can do all your style changes. Set line color, blue, turns it, for example, the blue line. You can try this in function 0.c. There you go. So we do this function. Okay. You can also use a user-defined function, a function you define, okay? Not limited to that string, a more sophisticated function. For example, you define it as a C++ function. My fun, double x, is x plus sin x. Okay? This is the definition of my function. This could be arbitrarily complex, anything you want. And you can define your function object using this function. F1 of my function, okay, from -3 to 5. This, and can draw it. This is function 1. Of it and draws my function. Okay. So you're not limited to this, whatever you write to the string. You can put some actual code here, some C++ code here. You can also use tmath functions and with parameters. You can give them parameters. For example, here, my F3 function is TF1 object. This is how I define it. Tmath, lambda, okay, x, and parameters, 0 and 1. The lambda function is 2 parameters. And again, the domain function. And this is the step at which I create. Here, there's a typographic error, F3, but this should be F3. Okay, they will match. Bir hata yapmışım. Şundan aynı olması gerekiyor. İçin fonksiyonu parametreleri set etmek için. Then if we do redraw and we get our lambda function. The function call to team. We can get our lambda function. Okay. Next step is the root files. Let's try to understand them. They allow for the storage of data and objects on disk. It's a root specific file format. It also supports directories. New objects such as Histogram are created in a current directory. There is such a thing as a current directory. Okay? So You can use this command, create a root file. Okay. The T file, select this new T file, my file. You've already seen a command like this. Then, using this pointer F that points to this file objects, we can create your directories. NK1 bizim, okay? And it tells that directory, gives you a pointer to that directory. Okay, and you can browse that directory in the root object browser. So, and you can use this list method of the file object that it gives you what's inside, what objects are inside the root file. For example, okay, this is my file object, and there's this key which I just created, the key directory. Right? Easy. Now, how do I change directories? For example, I use just like Unix command cd change directory. I can change to it easily. Result is true. That's successful. Then I use print working directory method of G directory. It is myfile.root/busy. Currently, I'm in this root file, and I'm under this directory. So whenever I create a new histogram, it will be created under that directory. Okay? When I will browse it, it will appear under that directory. And I say ls list, my directory will be displayed there. Okay, this was about root files. Now let's continue with root trees. So root trees are objects. They are data collections, organized data collections. They are used for storing large collections of objects. Okay. It can be, for example, experimental data, simulation data. So it's the most common use of design case of root trees. So the concept of collision events is very important in particle physics. Okay, so an experiment is a sequence of events, and so root trees store sequential event data. We use root trees through these objects, T3 and TN tuple objects. Okay. TN tuple is like a simplified version of T3. T3 can store any object and any data type. Okay. On the other hand, TN tuple can store only floating point numbers. It's also a common case. Okay, you usually just want to store some numbers, so TN tuple is quite useful. But when you have more general cases, like if you want to store some physics objects, then you can go to root tree. This is the structure of a root tree. This is an event, a set of data. There are these variables, x, y, and z. Okay? In a root tree, every variable has a so-called branch, W, arch, another W. Okay, and so each data instance is a leaf. Her bir data noktası bir yaprak. So we have a number of branches. Each branch has a sequence of events of numbers. Numbers come from events. Okay. This red box is an event, just shown here. Okay. The root trees consist of branches and leaves. You can visually inspect them with T-browser. And data in root trees can be analyzed, actually analyzed. Now you create a tree. You can use the T3 viewer grids. Okay. Again, it's a graphical user interface. Here's an example for creating a tree object and writing data in it. It's in the macro tree.c. First, let's create our root file. Okay. Root file opening. Okay. Now I have my root file. It's f pointer. Now let's create the root tree. The class, relevant class is t3. Its name is events. Okay. This is the title, event tree, label. In the pointer t. Now, what will I put in this? What data will I put in this tree? Let's have three variables, okay? Three branches. First variable will be an integer, variable 1. Floating point variable, variable 2, and 3. Two floating point variables and an integer. And I define my branches in the T3 object, okay, using the branch method. This is my tree object, okay, branch, the name, variable 1, okay. This is the address of my variable. So it's very important that I define this branch with the address of the variable. So it will look at this address and get access to data from there. And here, again, this is the name of the variable and the data type, integer, floating point, integer, floating point. So it must match the data in these variables. So, okay, now the tree is created. Now let's fill it with data. Here, I set my variables to these values. And I call this fill method of my tree. When I call it, tree looks at the memory locations of these variables, accesses these values, and fills the tree with those values. A second set of values, okay, variable 1, variable 2, and 3. Again, I call the fill methods, and then I do a print, okay, gives me an information about the tree, three objects method. T show method displays the events, okay, first event in this case. This number is the index, the event index 1. The important step is the write step. If you don't do this, it's not written into the root file. You call the write method, and then you close your root file, and there you go, your tree is now stored. Let's do this. This code is in the macro tree.c. Here we go. So this is the print methods output. Okay, these are the branches. It has two entries, two events. Branches. This is the first event printed. Event one. Okay, we can look at it in the object browser. Okay, events factory. Here, my branches from the and then the content of the branches, like a drawn like a histogram. Okay, so the data is written into the tree and the root file. So this was writing data, and about how about reading the data from a root tree. It's in this macro tree1.c. So first we need to open this root file. Okay, events.tree. It's now in this pointer f, and then we must access the three objects from within that root file. This was my root file pointer. Okay. I use the get method. Gives me the object. Then I give the name of the object, events or strictly object. It's root 3. And this is the data type, root 3 star, pointer to the root 3. Okay. Root 3 star. Let's say that I only want to access one branch, var 2. Okay. I don't have to access all of them. I set the address, branch address to my variable var 2. Okay. Again, address operator. Then I start accessing the data. Here I set up my loop on the entries, the 3 entries. This method gives me the number of entries in the root file, n entries. Okay. There were 2 of them, given method. Then I start my loop. I goes to from 0 to entries. Okay. And then I get I call the entry from this tree with this index I, 0th entry, 1st entry, and so on. Here I have only 2 entries, 0 and 1 first. When I call this get entry, the data is loaded into this variable, okay, because now its memory address is set here. When I print it, I get my values stored with tree. So we can look at this macro for accessing those data in a root tree. Okay, we are getting to the end. This is my final section, accessing root from Python. So it's very practical. I use it a lot. Root has interface for other languages like Python. The following code can be saved in a Python script file and run the Python interpreter using Python py-root.com. This is Python code, okay? In the Python code, I don't know how many of you know Python, but you first import this root module. Okay? Of course, your root must be compiled with support for Python. So you first import it, then all those objects are available to you in Python environment. So your canvas is root.tcanvas, okay? Age object root.th1. You create your histogram. You fill it with the Gaussian, okay? You draw it, and finally you save it. Okay, so let's try this. py-root Python. Here, as you see, I'm not calling root. Okay, I'm running Python. So here we go. Okay, this PDF file has been created. Let's look at it. There you go. 1,000 entries, and it's in the shape. Distribution is in the shape of a Gaussian. Okay. So it's a practical way to access root. Now let's mention the other root libraries. What other libraries you have access to? Okay, there are the mathematics libraries, math4, math.mo, Human. For you can create network connections with these classes, T-socket and T-server socket. You can do parallel processing. Okay, you can do your computations using two parallel. You can distribute them to multiple CPUs or threads. There are those classes for physics vectors, very useful. There are classes for graphical user interface, data frames, okay, which I mentioned before, geometry, RuFit, and TMUA, machine learning interface. It's quite mature and quite extensive. You can do many things with it. Here's like a diagram showing what these libraries can do. There's a math core, physics vectors, complex numbers. T-random is part of math core library. Basic functions. Okay. Here, some examples to what you can do. It's the drawing of the Alice detector at LHC, created with you, designed and created with you. This is an example GUI, graphical user interface. You can write such programs in it. Do your plots, okay, multiple ways. Do your fits, and so on. Here are my main references. Okay. You can consult these for further information. I will also upload these slides to the Google Drive folder, so you can also go back and look at the slides. So that's it for me. Do you have any comments, any questions?